So we're here to talk about practical rail stress management today. Okay, so I won't go through anything about myself. Obviously, we've had a brief introduction, but I've been involved in track maintenance since the late 90s. So I've seen it done right, I've seen it done wrong, I've seen plenty of issues with stressing over the years. So what we're looking to do today is look at stressing and rail management, or rail stress management, from a practical viewpoint. This is applicable to those who are new to stressing, and perhaps those that also need a recap. What we're not trying to do is regurgitate what would be a stressing course. It's really very much a practical viewpoint. As we can see here, the consequence of not doing it properly is the same result. Your track buckles and your trains cannot pass. So more serious consequences are when the track buckles and trains come off the track, as you can see in this picture here. And this happens with little or no warning. Generally, when track buckles, it will buckle under the passage of a train when it's under some dynamic loading. And of course, there's no particular warning for the following train. And obviously, the train hits the buckle, and you're likely to see a serious derailment if it's speed. So what we're going to cover today is how do we stress the rail, when we stress the rail, and what we're looking to achieve from this, the basic types of stressing and traditional methods that are available, the basic steps in the operation, and then more importantly, what are the practical considerations around the planning, any constraints that you might face, and any site characteristics that are important. And then what does catch us out so often when we do stressing? Stressing is a task that's pretty challenging to do and can quite easily go wrong if you don't follow a number of clear steps, and we'll look at those towards the end. So how do we stress the rail? So when we stress the rail, we usually do this after a track renewal, when we replace the rail, especially when we do long quantities of rail. Removal of rail defects that are in stress track. If we decide to remove a set of expansion switches and increase the amount of stress railway that we have. If we have a broken rail, if we have a bank slip or disturbance or some sort of buckle on the track. Any significant changes in the geometry of the track. So if we decide to tighten a curve or flatten a curve and we create more length of rail. And ideally, in an ideal world, you'd re-stress your track every 5 years, although I would imagine around most of the world, this is rarely occurs, and from a budgetary point of view, is very, very challenging. So what are we looking for when we want to stress the rail? So we're looking to achieve what's called a stress-free temperature. And a stress-free temperature is when the rail is neither in compression or in tension. In the UK, we look for a stress-free temperature of 27 degrees C, but this will vary around the world based on your ambient climate. We're also looking to achieve consistent stress along the rail. So if the one part of the rail is in tension, we want the other part of the rail to be in tension. So we want consistent stress all the way through. All your stressing as well should be set up and delivered before the onset of hot weather. So every summer, obviously. And delivered in suitable sections according to time, access that you have to the railway, and the resources that you have available. So we have several types of stressing. We have mechanical stressing, which is level 1 and level 2. Level 1 is stress restoration, which we're not really going to cover today. And level 2 is complete re-stressing, which is the main focus of this talk. We also have mechanical stressing, and that's pulling of the rail using hydraulics. And then we have thermal stressing, which is using either heating the rail or using the natural ambient temperature around you. And there are some various techniques called rail warming, which can help to do this if the natural ambient temperature isn't around. But these aren't used very often in today's rail industry. So level 1 stress restoration. So this is what it says on the tin. It's restoring the stress to its current stress-free temperature. So it's used for the installation of short rails, potentially a closure rail if you're doing such like a rail defect, for instance. And what you're doing is it allows you to maintain the stress in the rail in a single shift. It also gives you the ability to give an approximate indication of what the stress-free temperature is in your track. But regular use of stress restoration on a section of track can degrade the SFT, or the stress-free temperature, over time, and that can either make it become too low or too high, depending on how accurate you are at doing it. But with stress restoration, it's only as good as the stress that's in the track beforehand. So all you're trying to do is return the track to the position it was before you made the cut into the track or into the rail. So level 2 stressing, well, that's restoring the stress to a predetermined SFT, or stress-free temperature, over a controlled length of track. It's very accurate if done correctly, and it's not dependent on the condition or the rail stress that was in the track prior to the works that you're doing. It's generally used on the installation of rail greater than 20 meters. So if you're doing maybe installing strings or from a track renewal, then that's the ideal application for this. So mechanical stressing, this is where we physically pull the rail. So we will grab it in 2 clamps and pull the rail together to a predetermined set of dimensions. So we're looking to induce stress equal to a stress-free temperature of 27, or whatever the limit is within your local area around the world. And the way the calculations work, it's based on the difference between the ambient rail temperature at the time of the operation and the desired stress-free temperature, which is classed as delta T. So if you have a rail temperature currently of 17 degrees, then you're looking to induce an extra 10 degrees of stress into the rail. The only criteria for the UK is that because the stress-free temperature is 27 degrees, when you undertake the operation, the rail temperature must be below 27 degrees. So if you try and do this on a bright sunny day in the middle of summer, you'll find that the operation you'll be unable to do the operation. So the equipment you use, so rail is placed on side and under rollers. This allows the rail to be able to move when you pull it freely. You have hydraulic rams that pull the rail together. These are usually powered by a petrol compressor that's taken to track by hand or on a trolley. There are also lightweight hand pumps available in emergency, or if your compressor breaks down. But it's certainly a very hard operation to use a hand pump to stress track. You'll certainly have a sore arm afterwards. So with the rollers, as I said, the rollers allow the rail to move freely, and this allows you to induce an even distribution of stress through your rail. As you can see from the diagram here, if you try and pull a piece of curved rail, what's going to happen is that the apex of the curve is going to want to move inwards. So the idea of the rollers are that they also retain the lateral movement of the rail whilst allowing it to move longitudinally. The spacing of these rollers is also dependent on the geometry of the track. So the tighter the curve, the more rollers you'll need to retain its position. So traditional rollers in the United Kingdom and probably most of the world, on the left you'll see an under roller, and that simply sits on top of the sleeper, and then the rail will sit on top of that roller, and you set them up so when the rail moves, it will move the roller from left to right in the picture that you're looking at. As you can see here on the right, you've got a side roller, and that roller is designed for traditional pandrol housing and will just sit in the housing and stop the rail moving inwards whilst you pull the rail longitudinally. In more recent times, we have things like Vortop rollers, and these are designed for use with in-house or in-clip housings, such as a fast clip that you can see here, and these literally just sit over the housing and clamp in to the roll. And these will act as an under and side roller in the same thing. So you'll see the bolt on the outside. All you'll do is you'll turn that bolt and it will automatically lift the rail up off the rail seat, off the rail pad for you. These are probably more common in the UK nowadays. So this is a standard stressing kit. On the left, you'll see the saddle. You'll have two of those, one either side of the point of stressing. And what happens here is that you'll see that there's two holes on one on either side. What will happen is that your bars will fit in there, and it will just use the pulling action of the hydraulics to clamp the saddle around the rail foot. To the right, you've got a hydronic ram. You'll have two of those, obviously, and those will then pull the rail together. If you need some additional space, you can have some extension bars on the left, and then on the right here you've got a typical compressor power pack. You'll notice there's a little handle at the back of it, and that's the hand pump should the compressor unit fail. So the picture here, you can see a stressing kit that's been assembled. So you can see either side of the row, you've got a saddle with your two hydraulic rams and then your two extension bars, and this allows you to then put a saddle either side of the weld that you're trying to pull against. There's other types of stressing kit around. So this is kind of like a handmade stressing kit. So this is done by using bolts to or mechanical means to pull the tracks together. This isn't used very rarely in the UK these days. So natural stressing, this uses the ambient air temperature to heat the rail. So you still prepare the track in the same way, where your rail must be on rollers. And all you do there, rather than pulling the rail using hydraulics, you just monitor the rail temperature until it gets between a specific operating window. So in the mainline railway in the UK, this would be between 24 and 27. On London Underground, the range is slightly greater, to 21 to 27 degrees. And all that happens is when that rail is in that window, your teams go through, clip it all down, and then you undertake your welding at the very end. So the limitations for natural stressing, well, it's dependent on air temperature. If it's too hot or too cold, it's relatively difficult to plan. If you have some uncertain weather like we do in the UK here, it can be somewhat challenging even in the summer. And obviously, it can induce some uneven stress in the rail. This stress may roll out after the passage of trains, but it's not quite as accurate as it would be with mechanical stressing. One of the other issues you have is that the rail can change temperature while you're clipping it up, and then this is how you get induced some of the uneven stress into the rail. Some of the risks: by the time you've clipped up the rail, it may be outside the operating temperature window, which means then there's potential that you have to come back and stress elements of it in a traditional fashion. Rail warming. So this is very rarely used in the UK. In fact, I've never experienced it here, but it is still used across the world. And it's the same principle as natural stressing, but all this does is use gas heaters to warm the rail. Again, you can induce some uneven stress as the rail cools after the heating process, which is why it's not quite as good maybe as natural stressing. There's always a potential to damage rail-mounted cables and rail-mounted furniture, such as axle counters and other things, because you're effectively inducing a flame to heat the rails up. As I say, it's not common practice in the UK today. However, back in the old days, there used to be a trolley with a guy with a bike on it. This is from the UK in many years ago. You can see to the bottom left, there's some sort of metal covers that sit over the rail on some wheels, and those have got gas flames underneath to try and heat the rail to the temperature you're looking for. So I wouldn't have thought that would be allowed practice today, however. So level 2 stressing. So it's the process of mechanically inducing stress into the rail, as I said previously. This can be broken up into 10 key steps. First of all is your site survey, so understanding what you've got, what you need to stress, and any other elements of the site. You need to select your anchors, how much you're going to pull in one go, and more importantly, where your pulling point's going to be. and we'll cover all these in a bit more detail shortly. You also have marking up of the site. So when you go there, you understand what you need to do, where you need to put things. You then have to unclip your rail, install your rollers. You need to ensure your calculations are complete and they're still relevant for the ambient conditions that you have. You then install your stressing tensors and rams and pull the rail, and then you weld the rail according to standard thermic practices. Once the weld is cooled and up to strength, you then remove all your rollers and clip the track up. And finally, you remove the stressing kit once your welders give you the okay and that the weld is of a suitable strength based on manufacturer's instructions. So the site survey, and this is probably the most important part, and it's one of the elements that many people don't do properly or cut time on, and it's usually the one thing that can then cause the job to fail or come unstuck. So you really need to understand your rail, sleeper, fastening type. These are very important because they sort of indicate certain limitations of what you can do, what rollers you can use, etc., etc. Track geometry is very important, and that will tell you how many rollers that you need, how depending on the tightness of your geometry. If your curves are too tight, you can't stress at all. So you really need to understand all this accurately. The location of any IBJs, especially 6 holes that we have in the UK, because these are obviously linked to signalling equipment. Condition of the components. Is the track fit for stressing? Will the keys come out? Are any of the sleepers collapsed? Is it voiding? All sorts of things like this. So are the components fit for stress, as I said? Are there any tight jointed plates or insulated joints within the stressing site? If there are these have they got the suitable high tensile bolts? Are they in good condition to hold the stress? Are there any defective rails? Stressing a rail defect can cause a rail to fracture if it's serious enough. So any rail defects should be removed prior. Are there any expansion switches? This will also tell you where the limits of your site might be. One of the most important things is ballast level and obstructions. If you've got too much ballast in the way, then undertaking a stressing job is nigh on impossible without causing significant hassle. You get ballast stuck under the rail, all sorts of things there. So you really need to make sure your ballast level's nice and clear. Any cables that require disconnection between the signalling system, have they got enough slack to enable the rail to move a little bit, and can you reconnect them in the same place? And lastly, where are your access points? When you want to take a stressing job, you have to carry quite a bit of kit to site, and also get quite a few men. So it's as we're planning any sort of standard rail job, understanding where your access points are crucial. So this is the standard setup for a stressing job. If we go from left to right, you'll have an anchor. So this is just a piece of railway, the track that we use to pull against, and these are a predetermined length as well, to ensure that you don't just pull the track all the rail sort of out of their housings. You then have your pulling lengths. So this will be, so with any stressing job, you have two legs of a pull, and these are either side of what you would call the pulling point. And the pulling lengths have to be a particular length based on curvature, etc. And then lastly, you have a second anchor, which is the second point of restraint that you pull against. So the anchors, they're specified minimum length of secured rail to pull against. So the length of anchors is very much dependent on your components, your component type. It's generally 90 meters, and it's 135 meter from any expansion switch or traditional base plated timber sleepers. It can be 30 meters or three sleepers per degree change, or delta T. Whichever is greater for the high toe low clips, such as E2000, E plus, fast clip, Voshlow, all the modern sort of clips. And this is based on UK standards. This may vary depending on where you operate around the world. So you're pulling length. So this is classed as the length of free rail to be pulled in each direction. As I said, the length of L1 depends on track curvature. It's generally got a maximum of 900 meters, but it also has a minimum of 90 meters. Although this can be 180 if you've removed expansion switches. The network rail standards are quite specific about how long these legs can be, dependent on the curvature. So you can see from the table 4 here, as your curvature or the radius of your curve increases or decreases, sorry, so the maximum length that you can stress on any particular leg also decreases. So the pulling point is where we basically pull the 2 pieces of rail together. Ideally, it should be in the centre of your site, but this will also be determined by if you have a lot of curvature nearby. But generally, you should always try and put it in the centre of your site. If you're stressing reverse curves, for instance, then the pulling point should try and be round about the reverse point, and this allows you to then pull against the 2 curves a little bit more evenly. So how do we mark up the site? So we have 3 areas that we would mark up. We would first have the outer telltale and the inner telltale. So the outer telltale is designed to check the stability of your anchor. So ideally, you should get no movement at all with your outer telltale, and that would show that your anchor is held appropriately. The same with your inner telltale. So that's the very start of your anchor. You can get a small amount of movement here when you unclip all the rail, and you can add that to your calculations in due course. Then you have a number of reference points, and these reference points are calculated, and the idea is that this will determine how far your rail should move at any particular point along your length of free rail. So by understanding these, you can mark these against the sleepers, and then once you've completed pulling the rail, you can go along and check that your rail's pulled evenly, consistently, and to the right length. If, for instance, maybe your reference point 2 hasn't achieved its mark, but reference point 1 has, then there may be some sort of obstruction that's stopping the rail moving freely. So they're really, really good reference points to allow you to ensure that you've done everything as you should do. So cutting of the rail, if you're cutting into existing track that's already stressed, the first cut should always be a flame cut. All other cuts then are done by machine, i.e. disc cutter, to make sure that they're all accurate. But the first one should always be via a flame cut. When you're unclipping the rail and installing the rollers, so the rail is always unclipped from the cut towards the anchor. And this is done for safety reasons. So if you did it from the other end, all of a sudden your rail could jump because you've still got induced stress at that particular end. So you always go from where you've got you always cut, and then that's a safety method to make sure your rail can't pull or jump on you. You should remove all the insulators from the rail housing. Then the rail's lifted and placed on rollers. As I said previously, some of the more modern rollers now allow you to place the roller on the housing, and then using 2 sets of spanners, it will automatically pull the rail up in the air for you. You should remove the rail pad at any particular roller location. And your side roller frequency, as I said previously, is dependent on the curved radii that you have. And they should always have side rollers placed on the inside of the curve. Non-straight track, you would place the side rollers on alternate sides, each of the locations based on the frequency that you need. So as with the length of free rail, the amount of or the frequency of rollers also increases as your radius decreases. So as you can see here from the table 3, if you've got a radius of 1,000 to 800 meters, you need a side roller every 8 sleepers. And you can see from the right of the table, as you start getting tighter, the amount of side rollers that you need increases significantly. So this is one of the main considerations you need to have of how many rollers you might need and how big your stressing site should be based on this. So site calculations. So one of the key things you need to understand is what the rail temperature is at the time of the stressing. So traditionally we would have the analog or dial thermometers, which you'll see on the right, and you'd always have 3 of those, or at least 3 of those, that you'd place along your site. This would give you the indication of what the rail temperature is at various locations, but also ensures that if you have a defective thermometer, you can understand if you've got one different reading to the other 2. Okay. With the site calculations, well, the rail temperature allows you then to calculate your total extension, so how far you've got to pull the rail together to reach your stress-free temperature, and also the extension at your reference points. It'll also give you an indication of the pull force you'll need with your stressing kit, with your compressor, but we're not going to cover pull force or anything today. So site calculations, I'm going to spin through this bit quite quickly. There's a set of calculations in here which I'm not intending to cover today, but they're left in there. So when you look at the presentation later, you can use them for reference and work your way through should you want to. So if we look at this particular site here, we've got a 90-meter anchor at either end, and we've got a length of free rail, which is 700 meters. So if we used to do our site calculation, we would generally break this up into 100-meter sections from our inner telltale. So this would give us 100 meters to reference point 1, another 100 meters to reference point 2, another 100 to reference point 3, and another 50 to your pulling point. Then you give you some regular intervals for you to calculate your reference points. Okay. We've also assumed an air temperature of 17 degrees for this particular example. So going through the calculations, the total rail extension for this particular example would be 137. So this would be 137 millimeters. So this would be the amount of rail that we need to cut out and pull against. So using the same calculation, you can see that each of these reference points, we would need, we would be able to mark on the sleeper 20 millimeters, 39, and so on and so forth when we mark the site up. So how do we monitor how far we've pulled each reference point? Was very, very simple. You literally put a mark against the housing on the sleeper, and then when you've pulled the rail, hopefully it will move to the other mark, and then that will determine that your rail's moved clearly and consistently in the right direction. It is very much simple as that. I'm a great fan of using coloured pencils that I've stolen from my children to do that. So but you'll find other people have different methods of doing it. But it is very, very much a simple case of marking the rail and then marking where it needs to move to, and that will give you a clear indication if you've achieved what you need to achieve. As I said there, so we've gone through this previously, but you can see the setup of the stressing gear there with the power pack, the saddle, either side of what would be your stressing point. So now we come to pulling the rail. So cutting the gap, you need to consider the following. So we need to know what the total extension is. So from our example, it was 137 millimeters. And then we need to consider the welder's gap. So how much do the welders require for their thermic weld? And that will be based on your local standards. And some welders require a 5 millimeter extra working gap. And you need to add all these things together and then understand how much rail you actually cut out before you start pulling. When you pull the rail, you need to check the entire length of the site. So obviously, if you consider each leg, the maximum we could have was 900 meters. That could be well over a kilometer of the site. So obviously, it takes a while to check, and this is one of the things you need to sort of consider when you're planning the job. As an engineer, having to walk up and down the site to check that all the rolls are installed, there's no obstructions, etc., can be quite a challenge. You also need to check that all your reference points are all marked up, and you also need to make sure that all your pressure gauges on your stressing equipment are working sufficiently. You need to be able to monitor these as the stressing operation undertakes. So when we weld the rail, we need to check that the rail is pulled correctly. So Once you're satisfied that all your reference points have been achieved, you fasten approximately 40 meters of rail either side of the stressing gear. This will ensure that there's no movement in the rail should the rail temperature change a little bit, or the ambient rail temperature or air temperature change, which might induce a little bit of additional stress. You also then need to check that your welder's gap is within tolerance for your welders. And then you place marks on your hydraulic rams, and this is to ensure that there's been no hydraulic creep in the ram, because this can sometimes happen where if the rams aren't maintained brilliantly, then sometimes the ram can leak a little bit of hydraulic fluid, and it can move the rail apart or towards each other accordingly. You then drop the rail and the weld and leave that undisturbed for a specific period of time according to the instructions or manufacturer's instruction of the rail of the weld. And then for sharp curves, fasten down should occur within 10 sleepers of any removed side roller. So you've got to be quite careful on sharp curves that you don't just go and remove all the rollers in one go, because that will pull, the track will just pull inwards. Okay, so you need to be very, very careful that as you start clipping up, you remove rollers as you need to. On straight track, that's a little bit less important. But the key thing is you need to monitor your gauges throughout the weld process, particularly the pressure and the pull force. If you're having to use a significant amount more pull force than you expect, then that would suggest that you have an obstruction somewhere that's causing you an issue. So once the weld is cooled off for sufficient time, which is generally around 30 minutes, the pressure can be released and the kit can be dismantled. And then you locally replace the clips and insulators around the weld. Then lastly, you complete your stressing certificate, which is perhaps the most important thing, and this is your record of what you've achieved. Okay, so you need to put your location, what the rail temperatures were, your extension calculations, any pressures or pull force that you had from your equipment, site conditions, whether there's any special features, and also include your stressing diagram. So natural stressing. Preparation of reference points are the same as mechanical stressing. When the rail is cut, the ends are splayed at the pulling point. Rails clipped up from the inner tail to the pulling point. When the temperature reaches an operating range, you literally cut your welder's gap and drop your weld at the required time. So practical considerations. This is the most important parts of the process. You need to develop your scope of works. So what you're looking to do, where you're looking to do it, and as I said previously, the site survey. Access availability, whether you can do it at a weekend, a midweek, how much access do you have to the track, and then also your labour, plant and materials. So what and where? Well, what are you trying to achieve and why? Is it a track renewal? Are you re-stressing because you've got a low stress-free temperature? Are you re-railing? Remove expansion stitches? You really need to determine what your stressing limits are. So what's the limits of your site? And then you can work out how you then break that down into manageable pieces. So the site survey, you look at the rail sleeper fastening types, what the rail section is. Depending on your rail section will depend on your coefficient of expansion in your calculations. So you really need to understand that, and then there will be certain coefficients based on that section. We generally have two in the UK, which is 56E and 60E rail sections. Sleeper type, whether it's concrete or whether it's timber, and then your fastening types as well. So what sort of housings do you have? What sort of clips, etc. Your track geometries we've talked about previously. Start and finish of any curves, where they are located, and then the hand and radius of those. So you need to understand. You need to take versins, etc., to be able to determine what your curve radius is. So one of the things that's always overlooked is the location of insulated block joints or insulated rail joints, depending on where you're from. So you really need to consider their location and how they've been installed. If you've put them in a track renewal, you put brand new rail in, you need to consider where you need to offset them in the bed first. So when you pull the track or pull the rail, that your block joint doesn't then foul a sleeper or a housing. And this is probably one of the one of the greatest things that get overlooked. This is even more important if you have 6-hole IBJs, which are very common in the UK and Europe. So condition of components. So are your pads and insulators worn? Will they be fit to stress against? When you clip everything back up, will they actually hold the stress? Are your keys in good condition? And this isn't all about the toe load, whether it can hold stress. It's whether you can actually get them out or not. The amount of times we've been to sites where in our preparation work, and you can't actually get the keys out because they've been seized because they may be sat in inclement weather for many years. So you need to consider whether you need to do any component replacement prior to doing the stressing. If you've got joints such as IVJs, then have they all got the high tensile bolts? Are your torque settings correct? Last thing you want to do is in the middle of a stressing operation, your bolts snap because they're the incorrect bolts. Are all your rail defects removed? And then other things to consider: ballast. Is there sufficient ballast? Will that hold the rail, especially on curves? The amount of ballast is very important. And on the other side of that, is there too much ballast? Is it going to get in your way? Are there any wet beds present? And are there any signs of voiding? Wet beds and voiding are typical locations where track can buckle as well. So it's important that if we're going to do some stressing or induce stressings to rail, that these are removed prior. Cables. So are there any disconnections that you need? You need to assess the amount of cables that require disconnection during the operation. And with disconnecting cables, is there any testing that needs to be done afterwards? And more importantly, will the cables refit the rail in their positions if you move the rail slightly? There's certainly on London Underground, a lot of the cables are particularly tight due to space. So if you do some stressing, it's not uncommon that the fact that you might need to replace the cable or be able to move it so you can reconnect it again. As I said, we talked about access points, about how close and how far away are they. Stressing plan. So you should always consider all the elements we've discussed previously, and you should have a clear plan that's got a diagram, it's got clear start and finishing points, where you're going to be, where your pulling point is going to be, where your reference point is going to be. That should also detail any prep work that's required based on the considerations prior. And you also need a plant list because you need to calculate the number of rollers and any small plants such as hand tools to remove keys, clips, etc. And your list of heavy plant. And more importantly, your spares. So do you need any new keys? You should always carry at least a small amount of sundry spares. Should you lose some in the process because it's dark or some of them fail when you're trying to remove them. And then you should program the works out, including hold points, to determine whether you can or can't complete the work. This is a typical stressing plan. It's very, very simple, but it gives you clear start and finish point, where your anchors are, and then where your stressing point would be. So why does it catch us out? And you'll be surprised how many times people have got caught out with stressing, or they've gone to do the job and they've never been able to finish it in the night. And it's down to three things, which is preparation, preparation, and preparation. So preparation number one, lack of attention to detail on the site. Some cases, no site surveys done. There's no identification of the geometry. That simply go to site and think, I can understand it there. And all of a sudden there's a curve that you didn't expect to see. The site conditions are unknown. So they might have wet beds, might be voiding. We've not done our drawings. We haven't done our initial calculations. So we're doing everything from scratch. We don't have the right plant, or it's not prepared properly. And more importantly, the site's not marked up clearly beforehand. So when your team go there to start unclipping, they don't know where they got to unclip to, or they unclip too much rail. Preparation number two. So any identified rectification works not completed. This is a very, very common problem. So sleepers are not lifted where voiding is present. So it's very difficult to put a sleeper back up to the rail once you've unclipped it and it's dropped. And it's very, very time consuming. Wet beds are also a big issue where the sleeper will drop. It's quite difficult to get back up. The pads, clips and nylons or insulators are not changed. And generally not laying out rollers prior to the shift in the cess or in a safe location. This can save a huge amount of time because everyone knows exactly where everything should be. And lastly, too much ballast, and it's probably one of the most common issues when going to a stressing site and going wrong. So, preparation number 3. Technical staff are unfamiliar with the site. As I said, just gone to the site for the first time. The calculations are completed from scratch. And that will generally be under pressure. Certainly in the UK, when we do this at night, you have a very, very limited time window where everything's mapped out to the minute. So trying to do calculations and measure rail temperature from scratch under pressure is almost guaranteed to ensure that you'll get it wrong. It's insufficient skill sets. So if you haven't got people that are familiar with the work, it can take a significant amount more time to do. And this is especially important when you're doing the unclipping or the clipping up operation. Insufficient plant, so having spares, fuel, lighting. If your compressor, not having a spare compressor, if you have to hand pump stressing or instead of a stressing kit, it takes forever to do. So having a second compressor is always important. Seized keys, pads sticking. And I say too much ballast getting caught under the rail. Some of the issues, too much rails cut out, so you're not accurate with your calculations, and all of a sudden you've cut too much. And we said dropped sleepers are difficult to key up. But the one key thing to remember is that especially on a particularly long stressing site, supervision is extremely difficult, especially if it's up to a kilometre long. It's a long way to walk to make sure everyone's doing what they need to be doing. So having the right skills and supervision is extremely important. But more importantly, if it all goes to plan, you can have a relaxing sleep after the operation. So, thanks for listening. Once we actually got started, and I guess it's over to any questions.
Thank you. I have a few written down that were sent. If anyone has any more in the meantime, just write them in the chat section. So the first question is, how long can you leave the track unstressed?
So if your track is unstressed and you have to make an assessment, and that's certainly in the UK, that's clearly prescribed. And that will be based on, again, your radius, the condition of the track, but it's more importantly based on what the stress-free temperature is at that time. So if you have a disturbance or you release the stress in the track, you need to make sure that you take the temperature at that point, and that will allow you then to risk assess. And then you have to monitor the rail, the temperature of the track, and make certain interventions based on those that risk assessment. So then you would either have people out watching the track if it reaches a certain threshold, or a higher threshold would be that you have to introduce temporary speed restrictions or even block the track in extreme cases. This is more of a risk in the summer where your stress-free temperature will naturally be higher anyway because the sort of ambient rail temperature is higher. But you should always try to re-stress the track to within the sort of prescribed limits at your earliest opportunity.
Second question, how far can you stress before it becomes a level 3 stressing?
Well, level 3 stressing is for S&C, so into S&C. So level 2 stressing is plain line. Level 3 will then be going into when you start stressing with S&C, and that's a significantly more complex subject altogether. And that very much depends on the components, etc., and the sort of the configuration. That's quite a complex operation that requires all the same steps that we've talked about today, but the calculation and the sequencing is a lot more complex.
And lastly, how often do we have to check the stress on rails?
So you generally won't check them if you know them. If you've got good records, then you wouldn't need to check the stress. But what you would do is every time you disturb the track, you would make a record of that, and then the idea is that you'd either return the stress using stress restoration, but you'd also have a record of all these disturbances, or you would re-stress in the method we talked about today, which then would return it to prescribed 27 degrees for the UK. But it's about record keeping, really. If you don't have the records, or the danger comes is when you have people disturbing the track in an uncontrolled fashion without keeping the required records to sort of state what they did and when they did it. And that's where the danger comes, where you start getting a change in your stress-free temperature that you don't know about. And that could be in a positive way, or that could be in a negative way. And that's one of the key areas where track buckles happen. You've induced stress that you weren't really expecting, or didn't understand into the track.
We have another one. It says, I know you haven't touched on level 3 stressing. However, can you complete level 1s with S&C without a level 3 certified person on site?
No. My understanding is that you would, to do anything in S&C with stressing, you would need to be level 3 trained, because you need to understand what you can and can't do within S&C as well. And as I say, there's quite a prescribed process that goes through depending on the componentry. But my understanding is that you would still need level 3 certification and understanding, and you should do anyway, doing anything in S&C. It's certainly not an activity where you should go in undercooked with technical ability.
When doing the calculations for level 1 stresses, is it normal for your OSFT to be an abnormal number?
Yeah, absolutely. It's because it's not an exact art. Trying to measure how much the gap's moved and where it is at the end of the free rail. If it's a small closure rail, it's quite difficult, and it's small changes in the dimension can have quite a large effect on the calculation because it's such a short distance. So it's not unusual to have those, but you would get a feel for whether it's significantly out. But this comes down to sort of accuracy of your work, how you mark up your rail, and how you measure everything. So obviously making sure that you do that process step by step. But it's not unusual for it to be over or under, because there is, as I say, there's quite a lot of inaccuracy. It should be a guide rather than anything else. But if you're getting sort of an original stress-free temperature of like 12, then that would suggest that you might have a sort of stress disappearing from the track at that particular location.
Also, this is a side question. We're trying to get hold of a bullhead under rollers, but can't find any suppliers of the equipment. Was just curious if you knew of any companies that would supply this equipment.
I don't, and I've not stressed bullhead for many years. It's a long time. But anyone that might be around London Underground may be a good person to talk to. But it's not something that's undertaken. There's not a lot of bullhead stress track left, to be honest. So so finding that kit would be quite challenging, I'd imagine. But it's certainly not something I've done for a while. But London Underground would be your best sort of place to go.
Okay. I think that's for that question. You'll have to get in touch with Roger as well, because he raised his hand when the question was asked. So
no, Paul, I was going to answer a separate question on sort of the heating side of it. You know, where you talk about natural stressing and then there's thermal stressing. Who's currently undertaking that activity? I'm just thinking more tramways have exceptional curves. and the standards don't allow you to pull. So it would more likely be either natural, and if you're unlucky, your plan B would be thermal. And I think that's where we're stuck.
I'm not aware anywhere in the UK that does that anymore.
Yeah.
So it's certainly, it's not something I've done. It's kind of there. It was put in the sort of presentation for sort of completeness and maybe some historical benefit. I would be surprised if it happens anywhere in perhaps some more of the developed railways. It may still happen in some of the further outreach places where they don't have perhaps as much kit or as established standards as we do in the UK. But I don't even know if it's an established practice in the UK anymore. Certainly not with nice signalling cables and equipment. I think back in the days where there's railways where there's a lot less signalling equipment in the track envelope. That might be more there, but certainly in the UK where we've got axle counters and all sorts of other odds and sods in the track, it's not. It just won't be a good idea. Full stop. I think.
Okay, should we conclude there? If you, yeah, I'll just end the video webinar. Thank you all for joining us today in this insightful discussion on the critical role of stressing in railway maintenance. A special thank you to our esteemed guest speaker, Paul Butler, for sharing his expertise, knowledge, and experience with us. As we move forward, let's take these insights back to our respective teams and organizations, applying them to improve our practices and contribute to the ongoing safety and development of our rail networks. Before we conclude, I want to remind everyone that a recording of this webinar, along with the presentation materials, will be shared with you shortly. We encourage you to continue the conversation and share your thoughts and questions through our platforms. Thank you once again for your participation. We appreciate your commitment to enhancing railway safety and maintenance practices. Have a wonderful day. We look forward to seeing you at our next webinar, which will occur in mid-January and will be a special 2-day webinar. We'll be giving more information on this later on this month. You can email us with any other questions or any queries on the emails that you have for us. Thank you, everybody. Have a nice day. Bye.